let's get started. So I'm here today to talk to you about security. I know this conference is more about software and concurrency and all different new ways to use C++, but I'm going to talk in a general sense versus using the adversarial mindset. And I'll explain that a little bit. Let me see if I can go to the next slide here. Wake up. Okay, I'll just do that. Okay, so first I'm going to talk about adversarial scenarios. We'll go over some vulnerability trends, exploits in the wild, and how you can use a couple of strategies to secure your development. But first, let me tell you a little bit about myself. My alias online is Malware Unicorn. I'm known for analyzing malware and producing reports. Currently, I'm working at Microsoft in the Microsoft Offensive Research and Security Engineering Morse. So I look at code all day, try to find vulnerabilities, and I'll go into that a little bit. Previously, I was at Red Team at Facebook, or now it's called Meta. So I got some red teaming background, and I've done malware research in the past for FireEye and Endgame, and I started out my career at the Department of Defense doing computer forensics. On the side, I do conferences. I've done Black Hat, RSA, DEF CON, and a couple there. I don't need to name them. On the side, I do DEF CON. I'm on the DEF CON review board, so I review a lot of the talks, especially the malware ones. And I teach malware reverse engineering on the side. So I really like to give back to the community and do a lot of my, use a lot of my extra free time for volunteering. And you can follow me on Twitter. I'm not as active as I used to be, but you can follow me there. So what is the day in the life of vulnerability research? I'm looking at 75% of code, most of my work day. The rest, I'm trying to instrument a harness, make POCs when I need to, or proof of concepts when I need to. And I do larger projects where I try to tackle major issues across multiple organizations. And then I write some tools on the side. So what is the adversarial mindset? This is something I've found really fascinating and I've taken with me from when I worked at Meta and red teaming. It's a mindset that's not actually taught in traditional institutions. Let's see if this will work this time. Okay. So what we're doing is we're challenging assumptions. We're using resources creatively and trying to understand what the attacker's motivation is going to be. So let's build a scenario. So your goal is to get a free cup of coffee. There are no rules. So think about it. How would you do that? So there's different types of effort you have to go through. So let's go with the easiest, low effort. Say it's an in-dine coffee shop and you wanted a free coffee, so you just dine and dash. Low effort. Now a little bit more effort. So some of these images were created by Midjourney, so they're not real people. So low effort, you can hop over the counter and make your own coffee, get a free coffee that way. Obviously, you can get caught, by the employees, so there's some risk there. Medium effort, you can use fake currency. You can even go the extra mile to make your own fake currency. So a little bit more effort involved there. You're running the risk of, getting caught by the FBI. And then medium-high effort, you could pull a fire alarm and have everyone, get out of the building, and you can just make yourself a cup of coffee and get a free coffee. And high effort, you can threaten an employee with violence. Obviously, that's not the way to go, but there have been red teams in the past that have done this, actually. And then finally, the extreme effort. You can cause an explosion and have everybody leave the premise so you can have your free coffee. I mean, that might ruin your chances of getting free coffee, but it's free. So we're taking this kind of approach when we're looking at, say, an app. So I made up this app just for this scenario. It's a UI app running as a medium integrity level. And it basically takes in a file, an image file, And then it serializes it and sends it to another service running as a high integrity level. Then it sends it up to the cloud, where it's doing OCR processing, so it can give the text back to the user. So we're coming back through and getting the text file. So what are some problems here? We're using the same approach, right? I'm the attacker. What am I going to look at in part of this app? So first, everything, you've probably heard this many times, and I've looked through most of the presentations in the last 5 years for this conference, and there's a lot of things about input validation, sanitization. Well, that's the main part we're going to look at is, as an attacker, can I modify this file to make the program do what I want? And you know, the easiest way in low effort is going to be giving it a picture. Is there any authentication? Do I need to authenticate to the cloud? Is there any type of login in the UI app itself? Can I bypass that? Is it parsing the image there? Or is it parsing the image back in the cloud? I don't know. It has to serialize it somehow. Is there any shared data access? Obviously, you have to transfer that serialized data to the service, so there's some type of shared memory there if that's the way you want to go. And then, not only that, you have to worry about your resources that are on the file system. Can I use a DLL, like a malicious DLL, that is not verified on load and start running things in the program? Or if is it using a configuration file, could I modify that file in order for it to ruin its parsing? I don't know. Again, as it's coming back from the cloud, you got to think about the deserialization. This is where a lot of bugs happen, especially out-of-bound writes, fuse after freeze. And then making sure if any inter-process communication interfaces are locked down. Most of the time when we're trying to escalate privilege, we can directly access those if they're not locked down. And then, is there any type of protected cache? So sometimes you've got multiple processes running, and it's using a cache to store images and then sending it up to the cloud. Maybe it's caching things on the file system somewhere. Can I access that? Has it been locked down? Can I modify it? And then think about the service. And a lot of the issues I'm going to talk about are Windows-based. So sorry for the Linux folks, but everything will apply with Linux as well. So do you have a process that's running isolated? So say you're running at session 0, could you access another user's session if you're having multiple users on the same computer? You're violating the user isolation model. And then, is there any authentication that needs to happen between the service and the cloud? Can I directly try to mimic the authentication directly to the cloud and bypass the whole process from loading an image? And is the PII data on the cloud being isolated or protected? So those are the kind of risks that we're looking at. So now we think about the attacker's motivation. When we're thinking about privilege escalation, usually we see ransomware gangs. Ransomware, if you're not too familiar, is basically software that encrypts all the files on your computer and then gives you a ransom note, and you have to pay them a certain amount of Bitcoin. I think the largest amount I've seen is 80 million in Bitcoin. And then there's advanced adversaries, and usually these are going to be nation-state actors, advanced persistent threats. And then game hacking. Obviously, if you're trying to get around the anti-cheat engine, you're going to have some type of privilege escalation to do so. So what am I going to be looking at if I'm an attacker for privilege escalation? I'm going to be looking at all the different trusts, from untrusted to trusted, medium levels to high integrity levels. I'm going to look at the configurations, the file system, any way that I can get from a lower privilege to a higher privilege. And then now we're looking at lateral movement. These are usually done with people who are trying to go after finance organizations. One of the breaches I used to be on, basically they got in through a database, they traversed through the network to get all the way to the payment processors, and that's where they did the exfiltration at. So the important thing that they had was the lateral movement and being able to escalate, then laterally move. So we focus on code to be executed in different sessions, like I explained before. Is there any shared memory allocations? Can I get to an admin on the system and then start moving around within the network? And any use after free, we see that a lot too. Okay, remote execution. This is kind of like your worm type of malware that you'll see in the wild. And normally remote code execution attempts are done by advanced adversaries because they need the intellect to actually make the exploit to do that. And most of the time it's going to be deserialization, any client-server interfaces that are going to be poked at. And then finally, denial of service is we usually see with hacktivists, rogue hackers that try to go after organizations. Script kiddies, these are like really new 19-year-olds that find a script on GitHub and try to run it. And then game hacking, of course. If you don't like a server, you can always DDoS it. And so we're going to be looking at client-server interfaces for that. So I've kind of named a couple of different vulnerabilities, but now let's look at the trends. All right, some factors that influence trends. So we have an increased amount of security, where we've got secure coding practices, we regularly patch, we have a lot of testing. We're improving our bug hunting methods. We have fuzzing, we have structured aware fuzzing, we have fuzzing as a service. We're doing all of these things as part of our CI/CD pipeline. And we're having to combat this race between offense and defense. So as soon as we create a new security feature, there's going to be a way to bypass it. And so it's kind of like a back and forth cat and mouse game. And attackers will focus on high-value targets. So most of the time when it's like a financial organization being attacked, they're going to go after what can bring them the most money. And right now, ransomware is probably the biggest money-making attack out there. I mean, 80 million, of course I would quit my job with 80 million. But, I'm not a bad guy. Oh, go back. And then we have the introduction of cloud services, people working remotely, we have containerization, microservice architectures, we have more interconnected components, more features, and all of these new features we have to have backwards compatibility. And with Windows, we always have to have backwards compatibility. But there can be a lot of bugs there, like downgrade attacks. Okay, another thing is regulatory and pressures. So anyone who's worked with the government, there's going to be an executive order to have your baseline of security following their standards. There's GDPR for privacy to ensure that the user data that you're handling is encrypted, protected, and all that. California has their own Privacy Act. PCI DSS is for payment processors. They have the whole checklist that you have to do. And then HIPAA, obviously, healthcare privacy. So a lot of these influence how our security looks in our organizations. And then finally, we have advanced threat detection. We have the introduction of endpoint detection, or EDRs. We also have new compilers, security extensions to help us with some of these problems as well. And then finally, we have bug bounty programs. If you're in a big company, you should have a bug bounty program. And we'll get to that. So at Microsoft, we have the highest bug bounty is $250,000 for a bug. And these are in different areas. Just for remote code execution, which is like a worm-like exploit, elevation of privilege is 100,000, Hyper-V is 250, identity and authentication is 100,000. That's like a new employee. So there are incentives to find more of these bugs. And the problem is when they find the bugs, you're only given 90 days to fix them. I think that's the standard across the board. And if they don't fix them, they're going to release the proof of concept code. And when folks get the proof of concept code, they're going to use it in malware either the next 30 days or the following year. And you'll see it in the wild. So, and there are some upward trends. So memory safety issues have stayed dominant in the last 10 years. And I'll show you some numbers after this slide. Remote code execution, as you saw, they're very expensive. People want to go after them, make money off of them. Elevation of privilege, numeric errors, input validation, race conditions, and security feature bypasses. So I'll go into that a little bit. So I was able to compile this right before coming out here. And as you can see, the heap corruption on the bottom there has stayed pretty dominant throughout all the years, and use after free. These are probably the two most discovered Windows-based CVEs that we've been seeing over the years. So of those memory safety issues, we have heap corruption, heap read, use after free, arbitrary memory access, and race conditions. But for those who are not familiar with heap corruption, let's go over it a little bit. So how to create a heap corruption exploit. So when a program is able to access data outside of the normal bounds it was programmed to do, say it modifies the index, there's a bounds checking error, basically it's accessing data outside where it's supposed to. So what the attacker will do is it'll groom the heap, or heap grooming, to make sure data that is already present is able, the code that's being, or the bytes that are being added overlap the attacker-controlled memory. I have a little diagram here. Comb. So we consider this spraying. So we're spraying the attacker-controlled memory with aligned pointers because we know that the program that's writing to these locations is going to overlap at some point and and grab one of these pointers. The attacker releases the memory, writes to it again, and the memory hasn't been zeroed out. It's been corrupted ahead of time, and it can access those locations. So this is important when you're working with kernel, user mode, and kernel mode memory. And then the program performs a write over the corrupted memory or a read, and the data is overwritten in that address in a space controlled by the attacker. All right, so as I explained before, remote code execution, it's high value. I think although bug bounty programs do offer a good amount, there are other companies that will pay higher prices for them and then sell those to government entities. So you may not always get, a found exploit in the wild through your bug bounty program. There's an expanded attack surface. I think I explained this before. There's more cloud computing, remote work, interconnected devices. We're having complex software ecosystems, and there's more exploit techniques. We have exploit kits that are used by attackers. Okay, so if you're not familiar with the attack chain, this is kind of how we normally do an attack, like a red team operation. We're going to start with our reconnaissance. We're going to figure out some type of intrusion. Maybe it's an email with an attachment. Then there's some type of exploitation. But with RCE, we're completely skipping the reconnaissance and intrusion part and going straight after the exploitation. And then after we get to that point, we escalate our privilege, install ourselves, get some persistence, evade any type of security feature that's there, get a command and control, talk back to the server so I can write some commands to do some things, laterally move across the network to get to the crown jewels of the company, and then exfiltrate that data out. And then, so as I said, after the exploitation there comes privilege escalation. And why is that important? Usually it's for lateral movement. And it's also there for evading detection. Because say you have, you're running as a low IL process, you're trying to privilege escalate, but only medium or higher can do certain functions. So, and there's complex privilege models, and I'll go into that later in the slides, specifically for Windows. And then we have this concept in security called defense in depth. I don't know how many of you have heard that. It's basically a layering of defense mechanisms within your network or computer. And then finally, why security feature bypasses? Well, like I said, it's a cat and mouse game. As soon as we come up with a new feature, there's going to be another way around it. We've had ASLR. We found out ways to get around ASLR. We have DEP. We have secure boot. We've already had a couple of secure boot exploits. Sandboxing and hypervisors, sandbox escape, endpoint detection. One of the things that we used to do in red team operation was just turn off the endpoint detection, which is completely possible. Or you can get it to crash, your choice. Advanced hacker techniques, usually when we see these things, it's going to be used in malware campaigns, nation state, because normally they're trying to go undetected as they do their operation. And again, it's a race, it's a cat and mouse game, race between offense and defense. And then we have to worry about legacy systems and backwards compatibility. So a lot of the new features are being released with new versions of Windows, new versions of software, and if there's any type of file that needs this backward compatibility or interconnected processes, you're going to have to do a downgrade. And obviously the security feature is not going to work in that case. And so usually when you see the security feature bypass or actually use it in an operation, it's going to be either one of these areas of the kill chain. Okay, so let's talk about some exploits in the wild. I've picked a couple around heap management and input validation. So here's 4 different cases. We have the Nokayawa ransomware and the Bitter APT group, Print Nightmare, I don't know how many of you remember that one, and then we have the Raspberry Robin malware. So I'll go over each one of these. For the first one, I'm going to go a little bit in depth in the exploit, and then we'll kind of wean off from there. So the Nokayawa ransomware, who were they? It's a financially motivated criminal group that goes after retail, energy, manufacturing, healthcare, software industries. And here you can see the ransom note. Obviously, they've blurred out the Bitcoin address there. So what was the exploit that they were using? Basically, it was an elevation of privilege in the common log file driver. There was an out-of-bounds increment, and it was exploited on an attempt to extend the meta block within the base log file format. It could have easily been discovered by fuzzing, which was a shame because all you had to do was set up a fuzzer with the file input. The driver itself had a lot of try-catch blocks, And as someone who's looking for vulnerabilities, I actually look for those because those are going to tell me the best ways to find issues. Because we're trying to hide these exceptions within try-catch, and if the exceptions are not bubbling up, it's going to be kind of undefined behavior. So there was the access violation was actually suppressed. It wasn't able to bubble up, like I said, with these try-catch errors, or try-catch blocks. And on the side here, you see the base log format. We've got a control block and its shadow, and a base block and a truncate block and their shadows. And I'll kind of go into how this exploit was done. So first, you need to get the kernel address. Why? I'll go into the next slide. Second, you need to create a path for the BLF files, and then have another you have to create the BLF file and then modify it to trigger the exploit. And then you have to find the base block and get the kernel address from memory, and I'll show you how you can do that. And then once you add a log container, it triggers this whole exploit. And as I explained before with the heap corruption example, you have to use another BLF file to spray the memory in order for it to access that attacker-controlled memory location. Like I said, grooming the memory. And then having an out-of-bounds write. So in the end, we're trying to do privilege escalation, and I'll explain what's going on here. So why do you need the kernel address? Obviously for ASLR, one of those things you have to get around. And luckily with this nice Windows call, anti-query system information, you can loop through all of the kernel objects and try to find the right one you're looking for. Not only that, but you can get the function addresses that you need to compile your patched BLF file, because we want to force the execution to execute these functions. So we create the path, we put it in like a public file, a public folder, and you use create log, and it creates a file within that location. Now we want to modify it. So within this file, there's a base block. And in that base block, we have the header, the checksum, the base record, and a couple of records below that. And so this is the area we want to modify. So what we're doing is modifying how the record offsets are being handled. Here's the base record. So here's the modifications that are being placed there. I'm going to point out this address here because this is going to be our attacker-controlled address. So once you find the base block for the kernel address of the trigger base log file, you open the existing trigger file and then try to get the address pool size again to loop through the kernel objects in memory. And you're just checking the size, really. You don't need to actually have the name. Now in the control record, there's this CLFS metadata block, RG blocks. This is the actual array that is having the out-of-bounds write and out-of-bounds read. So we're trying to force the bounds checking to overwrite this array. So here's what RG blocks looks like. It's got all of these blocks in a 6-element array, and in those blocks is an image. It's offset and the type, and so we want to modify that as we go through. So when the driver allocates memory, it creates this block of memory that's about 90 bytes long, and it just keeps adding it as it goes in memory. This is important because we need to know where it's writing to so we can have our attacker-controlled heap spray access to the same location. So this is creating the log handle, and I'll explain what's going on here in the next couple slides. So we call add log container with the handle to the base log file. All right, now we create the spray. So what's actually happening is we want to modify this new spray BLF file so that the control block is modified in a way where if the out-of-bound block is being accessed, it's going to access that control block that we control. So we use pipes. We make hex 5,000 pipe pairs and then 4,000 pipe pairs, a huge block of memory. And then we overwrite that location with our log file that we just created to make the spray. And we keep looping through. So what's that going to look like? Once we free some of that pipe data, it's going to overwrite those meta blocks kind of sparse throughout. So in between where the attacker-controlled data is, in the dark purple, that's where we have all of these pointers that we've placed. So now in the attacker-controlled memory, we have a way to force the memory to our memory layout at this where it says referenced in trigger BLF. So eventually, we're going to be able to hit that location and execute those functions. So as soon as we modify to trigger the bounds, to trigger the failure in the bounds checking, it's able to access that location with our attacker-controlled data. So the whole point of this is to gain access to another struct within the block, the metadata block, that you can store kernel pointers in that location. And if it's controlled by an attacker, if that location is controlled by an attacker, we can grab that kernel pointer and reuse it for something else. So in this case, they're trying to go after the system process, grabbing the pointer to the token, taking that pointer and putting it into their own process to gain system-level privileges. So basically, you're able to write and read in kernel memory from userland. All right, this is just what I said here. Where they're using the dump count and the USN to trigger the bounds checking error. All right, so where the write is happening is in this struct within the meta block, the CLS container context. And in there, it has the PB container, which is where we put our memory layout before. I think earlier I just showed you offsets that it was writing to. This is actually what it's being written to. And like I said, it's looking for the system process token, and it's trying to copy that into the current process and get elevation. So this is a very complicated exploit, and it was found in the wild and turned into a proof of concept. And what the problem with some of these is that as soon as folks write a proof of concept, it gets adopted by all types of threat actors. Ransomware is probably the most used culprit because having privilege escalation is useful when you're trying to do lateral movement within the network. All right, the second one I wanted to talk about was bitter APT group. Why did they call it bitter? In their RAT, or remote access Trojan, they have this command and control packet, and its headers contain the bitter text. Basically, they're a South Asian cyber espionage threat group that's been active since 2013. They've been targeting Pakistan, China, Bangladesh, Saudi Arabia, those locations. And what they were using were in 2 instances of different exploits. One was, and a lot of these are going to be privilege escalation, as I explained before. It's very popular to move laterally within a network. And the first one here is an out-of-bounds write vulnerability in the DWM core driver, or not driver, Windows Desktop Manager, which has higher level privileges. The attacker grooms the heap the same way as you saw before. The attacker can control the data controlled offset in the direct composition API, and here's an example of what that is. So this property ID is something that they can manage from user LAN. So as you know, if you can if you can force the index to be changed to a new location, you can, do any type of read-write from, an attacker controlled memory, like I showed you before, with the heap spray having, user LAN pipes that can be accessed by the attacker. It's the same concept. They're using the same tactic. And the same goes with the Windows 32K bug. This one is actually a type confusion bug where it's trying to access a struct from a callback, and one of the offsets can turn an arbitrary value of memory. So if I wanted to find that system token again, I can use that struct to grab it. All right, this one is not necessarily a memory management exploit, but I wanted to highlight it because it's an RCE. So the attacker doesn't have to be within the network to actually trigger this. So what's happening is when a printer has an RPC interface, you can do it remotely. It doesn't have to be within the same network. It doesn't even have to be locally. So what they're doing is they're calling the RPC async add printer driver. And what it does is when you're looking for that, it's trying to add a driver within the network, and you can specify where that location is. And it doesn't have to be within the network. It allowed it to be called from outside of the network. So when it's being called locally, say the scenario is the user got this file from their email. The file was able to execute something. Then it calls the RPC async add printer driver. Then it's going to call out back to the malicious controlled server where the printer driver is, download that printer driver, and execute it. So you don't always have to be there locally to execute this exploit. So I wanted to point out is if you're grabbing resources from within a network or in a location that you don't manage, you definitely need to do some extra validation to make sure you know where it's coming from. And then, let's see. Finally, the Raspberry Robin malware. So this malware has been around for a long time and has changed over the years, but it's typically used by ransomware authors, or ransomware operators, let's say. Ransomware authors, usually they sell their malware, and then the ransomware operators buy it, and they have no idea how to use it. And you can tell the difference between, an author and a user. So in this one, they're using on the side there, they're using the same exploit as the bitter APT was using to gain privilege escalation. And they were using another privilege escalation with Win32K for an out-of-bounds write on an on-page pointer dereference. It's been used in a lot of different exploit kits in the past. And basically what they're doing is crafting a bitmap object to cause an out-of-bound target. And originally this was a POC that was completely basic. As you can see, I put the whole amount of code there. That was it. That was the POC. And so they crafted this whole exploit around just a few API calls. It's kind of sad. Okay, so now that I've kind of explained, the gravity of some of these exploits, how they're used by nation-state threat actors, how they're used by financial criminals, ransomware groups, and all that. Let's talk about how we can reduce some of these problems. So the first thing we always ask ourselves, what is your attack surface? So I work directly looking at Windows code, looking at the kernel drivers, looking at services and all that. That's my everyday. So when I'm looking at a new feature, I want to make sure I can figure out what the complete attack surface is before I start looking at everything. And to do that, you have to define the trust boundaries. So what is a trust boundary? I don't know how many of you have heard this, but it's basically when you have, you're going from an untrusted component to a trusted component. Same with lower level privilege to higher level privilege. So you want to make sure you draw that boundary. And some of the trust boundaries that we always first start looking at is any downloads from the internet, any network interfaces, any ports, drivers, any inter-process communication, COM, RPC, pipe, shared memory, parsing. Parsing is a big one. Deserialization goes with parsing. Any file system access. Is it touching the registry? Is it touching files, configuration files, images, blobs of data? Any sandbox interfaces. Now we've got the Edge sandbox. We've got Hyper-V. How can we do escapes? Well, there's got to be some shared memory port or port that can be accessible. And then there's authentication mechanisms. Sometimes you don't set up the authentication correctly. Maybe they're using a third-party open source library. Any type of logging. I think this one is overlooked a lot, where they're trying to send information back to their server to make sure the product is going correctly, but sometimes they don't do the authentication correctly or how they're storing their logs safely, and you can modify those logs as they're being sent back to the server. And then the other thing, we have a whole department for crypto, making sure that you're handling them correctly or using the right type of crypto algorithm. Have you set it up correctly? Are you using approved libraries? And then, of course, octals for kernel drivers. And then any messaging queue systems. This has kind of been on the rise with more technologies trying to make things faster. So we definitely need to know our attack surface. And to do that, we use a technique called threat modeling. I don't know how many of you have done this before, but I'll kind of go into how we do it. We also have a cool tool called Attack Surface Analyzer. I think this was created in the last couple of years by some of my coworkers. And you can execute that locally and try to evaluate your own application. And then we want to isolate problematic areas. Handling untrustworthy data. Just don't trust it. Anywhere you're touching untrusted data, like I explained before, you're going to have to isolate those from the rest of your high-privilege processes. Again, IPC parsing, network connections, those are the first things I always go to when I'm looking at a new feature. So what is threat modeling? Threat modeling is basically trying to map out your whole app architecture, very basic, and trying to define those areas where the untrusted goes to trusted. So let's kind of look at this. We have the same app as we had before. Now let's put it into a threat model. So we have the user input going to the app UI, the app service, and cloud. So here is where I would draw those trust boundaries. First, it's going to be the machine trust boundary. Anything that's from the file system going to the medium IL process. And then we isolate the app service with the high IL because we're getting input from both a lower privilege process, which is untrusted, and untrusted data from the internet. So we kind of have to carve out those areas where the trust boundaries are. So now that we know where the trust boundaries are, this is where we start to look specifically in those areas. For code, obviously we want to limit user input, period, as much as you can possibly do. Enable your compiler security options. We actually have tools to make sure that your binaries are compiled with some of these. And I'll go into that a little bit later. We want to reduce code complexity. I know there's a lot of talks about concurrency, but this is a really big issue, trying to minimize some of this where it's not needed. And then use safe and trusted libraries. And we'll go into that a little bit later on. And for the architecture, specifically on desktops and environments where you're using processes, we want to limit the privilege as much as possible. Have limited accounts. Maybe you have an account that has very limited capabilities or ACLs. And then we want to isolate untrusted inputs. So maybe that high integrity level process doesn't need to be parsing. Maybe we can take it out of the process and have it run as a separate process and then communicate there. And then management, we need to make sure we update our dependencies. Sometimes when we're using open source tools, maybe it hasn't been maintained in a while, or maybe maybe we're not using a modern library. And then if you're not already doing this, to make sure you have static code analysis built into your CI/CD pipeline. The idea is to remove as much overhead as possible for the developer to make sure that they're having those security checks as it's going to the code before it hits the customer. And then use fuzzing in your CI/CD pipeline. This is actually something new where we have fuzzing as a service, and it can be built into your CI/CD pipeline. I'll go into that a little bit. So now let's look into specifically like C++ development strategies. But I want to first talk about what the timeline is for Windows exploit mitigations. So starting in 2003, we have safe SEH, which is already by default on a lot of the Microsoft compilers. We have GS cookie, ASLR being introduced by default. We have the control flow guard, which is something you should always enable, but it's not enabled by default. And then we have ACG, arbitrary code guard, code integrity guard. Now we're getting CAS guard soon. I think they just, my coworkers just presented this at Black Hat not too long ago. It's still in the works. We have redirection guard, making sure that when you're trying to access a file, you don't want to have a redirect path. And then shadow stack. This is something that's used with the Intel CET technology. I think they just landed that last year. I don't know if we're using it yet. And then we have this new concept with the enclaves. So an enclave is basically where you can put control, like a secured area of memory that you can access and execute from. So the current defensive strategies is trying to minimize control flow hijacking. So being able to access or execute a pointer, attacker controlled pointer, we're then pivoting to controlling the flow on its own. And so we use control flow guard and the shadow stack to make sure that we can prevent those control flow mechanisms from happening. With arbitrary code generation, we've got the code integrity guard and the arbitrary code guard. And I have later on in these slides all the options that you can enable in the compiler. So one of the concepts that we try to do on my team is the rule of two. And this was originally coined by the Chromium team at Google. So basically what it is you have three areas. You're processing untrustworthy input. You're using an unsafe language. Unfortunately, this is CppCon, so it applies. And then we have, is it high privilege or there's no sandbox? So if you happen to have two of these things, and unfortunately with C++, you already got one, you have to manage the other one by either isolating it, reducing privilege, doing some fuzzing, etc. And I'll go into some of that as well. So I think I've been harping on this before with untrustworthy input. Any parsers, any JSON data, XML, anything that you're parsing, any deserializers, especially with deserializers, network streams, browser data, user input data files, all of these are untrustworthy inputs. And they shouldn't be running in a high integrity process unless it's a trusted source. So when we think about privilege, a lot has changed over the years with the introduction of cloud. Instead of having just ring 0 as kernel, now we have to worry about ring -1 through -3. So we have the hypervisor, the system management mode, and the management engine. And so those are lower on the scale for the higher privilege. Now for Windows integrity levels, unfortunately I work at Microsoft, so it's going to be Windows-based. We have untrusted, which normally we use for processing untrustworthy input, and we put those in a sandbox. We also have a low box, we call it, or LPAC, where we minimize everything around the sandbox process. It can't touch file system. It can only download things from the internet. It can't touch any resources, no RPC, no COM, just isolated completely, and it can only talk to the process it's meant to talk to. And then we have medium, which a lot of the programs that you see out there are running as medium. And I'd like you to know that medium is where a lot of malware likes to start from in order to privilege escalate. So whenever I see a new feature being, using a medium integrity level, I get kind of worried. And then for high and system, these are areas where you have to make sure that you're not processing untrustworthy input, especially in the system level. Okay, so going back to our app scenario, I've changed the architecture a little bit where I wanted to add this new handler exe for the deserialization coming from the cloud service. Instead of having that higher integrity level process doing the parsing, I take it out. Because it doesn't need it. And then I have them communicate to make sure the data is properly managed and then sent back to the app service. I've lowered the integrity level of the app service program because does it really need high? Does it need to access resources that are high? That's a good question to ask. And then I've changed the app UI to low IL because it doesn't need to have a medium integrity level. So I've changed the trust boundaries here. Now we don't have to worry about the higher integrity level process accessing data from the internet, which is great. Prevents some remote code execution vulnerabilities. All right. So some of the things to keep in mind: trust no one. Just don't trust anything. Don't assume anything and question everything. And beware of weak contracts. I think there's a talk later today that's going to go over contracts, so I'm not going to go into that much. I recommend you join that one. And always track the state. So these are the kind of rules that we try to live by when we're trying to develop new features and look at new features from my point of view. Okay, now for secure coding practices, pointers. The main thing I want to mention is validate all the time. Validate, validate, validate. Validate pointer address ranges before use. So, as I said before, if you're trying to if you're doing a read from a bounds outside of what you're supposed to be, you need to make sure those address ranges are validated. Any user to kernel data, So if you're trying to validate data in the kernel mode, you need to make sure you have enough validation mechanisms around that user mode data before you start processing it. And then index bounds checking. A lot of this can be fixed with using modern libraries, but always perform bounds checking on the buffers, on the arithmetic for the bounds checking as well. Avoid type confusion. I know this is hard right now. We're trying to develop new ways to avoid this, new libraries, new compiler mechanisms. But right now, you can use the GSL narrowcast and the WIL safecast. I know CastGuard hasn't been released yet, but soon, getting there. And then caller identity. This is one of the ones, this is more like an architecture thing. If I'm getting a callback, and I don't know where it's coming from, and it's coming from a different process, you can assume that it's going to be a malicious callback. So always make sure that the calling process is a validated one. And then finally, enums, verify enums with signedness. We've been seeing this a lot, and it's not always talked about. Using safe constructs, I think one of the biggest things that we always recommend engineers is to use a GSL span instead of a buffer, because you have more ways to check the bounds for the GSL span. And then for memory initialization, I don't think right now there's a C++ method for this, but in Windows we have the RTL secure zero memory to make sure the memory is zeroed out before use. So there's no corrupted memory overlap. And then null memory, you always want to make sure you have enough guards around anything that's null. Null structures, null pointers. You should always be checking your pointers coming in as an argument. And then bad asserts. Whenever I see a bunch of asserts, I get worried because asserts are not typically, or should not be used as ways for validation. And like I explained before with the heap corruption issue with the ransomware, try-catch blocks are big indicators of bugs. Whenever I see this in a future, this is where I look for issues with concurrency, issues with data access. I try to remove those try-catch blocks to see what's going on underneath. And then for denial of service, recursion. If you're doing any type of parsing, you want to make sure that your max depth is present. I've seen this with a couple of JSON parsers that I've been evaluating. A lot of the times they're going to have issues with the recursion. And warnings. If I'm looking at the code and I'm trying to compile it and I see people disabling warnings and all of these other warnings pop up, I get worried. Because when you're trying to suppress a warning, it's a sign that something is being done that's outside of the coding guidelines. And the coding guidelines that we adopt, and luckily some folks at Microsoft actually developed these core guidelines. I really recommend reading through these and applying them in your own development environment. Same with using the GSL library, since it's got a lot of nice to haves for buffer and memory management. All right. Now, as I explained before, there's a lot of these new compiler options for the Microsoft compiler. So we have, and some of these are not on by default, so you have to enable them. We have the control flow guard, the shadow stack. If you were trying to use ASAN, we'll talk about fuzzing a little bit later, you can do that easily through the compiler. EH continuation. If you want to verify digital signatures, so this is where if you're trying to load a dynamic library, you want to make sure it's signed, that it has a valid digital signature. Because if there's if there's a DLL hijack and you don't verify that it's not a malicious DLL, there's no validation at that point. All right, there's runtime checks, the buffer security check, and some of these others that are by default as ASLR and safe exception handlers. All of those can be added to your compiler options. And another thing, when I see banned functions, stop using malloc and memcopy. These are the ones that we look for bugs. Same with string cat, string copy. Your static analysis should catch this. If you're not already using this banned function list, you should add it to your CI/CD pipeline or even your IDE. So I have a link there if you wanted to go look at what the banned APIs are, but I don't want to go through all of them here. All right, now, like I keep saying, CI/CD pipeline, we at Microsoft, control GitHub too. So the Microsoft DevOps, they have this built-in tool to do binary scanning, CodeQL rules. These are rules that are designed for security issues that we've added over the years. Prefast and SAL annotations, OASIS static analysis results. You can run this locally as well. A lot of these you can run locally, but I recommend adding them to your pipeline. And then the C++ core check rules. All of these can be added to the pipeline. And it's just a configuration file. And if you're not already using them, I recommend turning those on. All right, so this is a tough spot for when I'm looking at third-party software, open source software. If you really want to use it, if you really got to use that CJSON parser, make sure that they have fuzz testing integrated. It kind of gives me a hint that they have like the security mindset. They already have a fuzzer running and checking their own work. It's a good way to get open source software approved. I think there's a movement going on where a lot of the parsers are being adopted into the Google Fuzz as a Service, OSS Fuzz. Ensure that the open source repository has good code maintenance. Check for the bugs. How often are they fixed? If the code hasn't been fixed in years, I would shy away from using that repository. And to avoid supply chain attacks, make sure that you are hosting an internal repo. We don't want attackers to modify those as well. And if you're hosting an internal repo, make sure you harden that as well. In your organization, it's tough to roll your own JSON parser or roll your own parser. You always want to use a library that's been vetted. And if you have a security team, I would have them check out the parsers that you're currently using in your organization and whittle them down. Make sure they're coming from a package, not copied and pasted code from another folder. So if you are an owner of open source software, I really recommend onboarding your code onto the public Google OSS Fuzz service. All right, now we want to talk about isolation. And I kind of showed this a little bit with the app scenario, where we have this untrusted process doing the parsing for us. It's outside of the process. That way it has its own address space to work with. We utilize sandboxing and this notion of app containers. I think I mentioned it before. We can have that as a lower integrity and do all of our nefarious stuff there. And I mentioned secure enclaves as well. Can we protect trusted execution and access to encrypted data there instead of, in a easy accessible process? All right, fuzzing. I think I've been mentioning fuzzing a lot, and it's probably the most most used way to finding bugs, especially the memory safety bugs. And when I mean bugs, I mean vulnerabilities. So I know in the past there needs to be this distinction between the two. So the easiest way you can do this is by using libfuzzer and address sanitizer. These are mostly for standalone processes. But if you have something like a client-server interface, I recommend snapshot fuzzing. And so what snapshot fuzzing does is you're creating a snapshot in time of when your client and server are set up. Then you can apply the fuzzer onto that client interface, and it can directly connect. And an example of this is What the Fuzz and Nix. This is starting to be a little bit more popular with the snapshot fuzzing, and it might be an area you want to look into. Structure-aware fuzzing. There's still a big issue with structure-aware fuzzing. We're working on it. There are some libraries to help with some of that. So maybe you have JSON code, XML, any type of structured data. We have libprotobuf mutator to help with managing that. And then I think I've explained this before, fuzzing as a service. So at Microsoft, we have OneFuzz, what we use internally as well. And it's open sourced, to set up a way to fuzz distributed. And this way we can integrate into our CI/CD pipeline. And OSS Fuzz is another example. So one of the problems that we have with the adoption of fuzzers is that sometimes developers get too scared to set up their own fuzzer. And with a small team of 70, we don't have enough time to go to every developer and say, here, I'm going to help you set up your fuzzer. I'm going to sit there and read your code and try to set up your fuzzer. So we have a self-service. And making a fuzzer, or setting up a fuzzer counter is not that bad. As you can see here, this function for libfuzzer, it's just one function that you just have to set up. Where your data input is coming from, that's all you have to do. And then set some compiler options. The bar is really, really low. So I recommend trying this out with like a simple program and doing it at home or at work. I would do it at home, because that's me. All right, this brings me to having developers have a security-focused mindset. You want to consider security at the start of your development, the design phase, where you're doing threat modeling and in the beginning, making sure that your design is good from the get-go, so later down the line, you know what your attack surface is, you know where you need to put the effort in for fuzzing or security reviews. Know your trust boundaries. Look at the attack vectors that you have and lock those down. Build attacker scenarios. Like I was explaining in the beginning of this talk, you kind of want to go through this exercise. Hey, I'm the attacker. How would I attack my own program or my own feature that I'm writing? And then always challenge your assumptions. So assuming that you're going to have perfect concurrency. There's not going to be any use after freeze or access to locations that you shouldn't be accessing. Don't assume that. Verify it. Using tools, whatever it is. You want to sit there and debug it? Go for it. I think I just recently found one, or earlier last week actually, where using coroutines and smart pointers or safe pointers. The WinRT pointers and the safe pointers don't actually know the reference counts. They have no knowledge. So when you're using them together, you're going to have issues where the calling functions memory is going to get released before the actual object is going to be accessed. So I recommend really testing those in different environments and not just a VM. Okay, final takeaways. Adopting that adversarial mindset, going through those scenarios, identifying the vulnerabilities of your feature. Think like an attacker. Go find your red team of your company, work alongside them, have them look at your stuff. If you have a security team that does security reviews, get involved. Make sure you're using the right libraries, like the GSL library. Try to get a lot of these things built into your fuzzing pipeline, especially when you have a lot of developers working on the same code. You want to make sure there's not as much lift for having to do all of these things locally. Stop it, before it hits release. And then, like I said, engage the security teams early. Work with them closely. Make sure you have a bug bounty program for your feature, if possible. If not, talk to your VPs trying to get that created. And follow security trends. I think there was a crazy news article recently about a supply chain attack with pagers. So supply chain attacks doesn't have to come with like physical hardware. It can come with your software. I think we've seen that a lot with some of the major exploits in the past. Was it Log4j? I think there was one. All right, some of my references. And my team logo. So that's all I had. I was going to open it up for questions. I know this wasn't too heavy on C++, but very heavy on security issues. So feel free to ask. Go ahead.
Hey there. Yes, this is a programming language conference. And in the past couple of months, there has been a lot of talk where like the programming language has been gotten a lot of blame for security vulnerabilities. People have been saying that like you shouldn't use a language like C++ in security critical environments. And you've shown a bunch of like mitigations that we can do to like diminish that problem, but like what is your take on this? Like how big a part does the choice of the programming language actually play here? I don't see it as a faster adoption. Like Rust, I think Rust is one of the ones that people say they're going to replace C++. I can't see that happening very fast. I still see C++ as like a major part in a lot of like backwards compatibility, a lot of programs to move faster. I think Rust has a lot of overhead as well. So I can't see that changing too quickly. But I think some of the reasons why it's been changing is a lot of regulations around using memory-safe languages. I think CISA had instituted that at our, as you saw the rule of two, it's one of those problems. Thank you.
Mm-hmm. Go ahead.
Hi. You mentioned at least twice in your talk that try-catch is a bad model, or that's something that you look at. And I think that we've been hearing a lot about error handling at this conference. And I was curious about like, what is an alternative that you prefer, or why do you, can you articulate more about what you have against try-catch?
Yeah, I recommend feeling early and bubbling up the error instead of, waiting for the try-catch to happen.
Hi, so in one of the slides, I believe it was mentioned that we should not use asserts as a way to validate, but can you elaborate on that? Like in my understanding, if I have a converter function that returns a return code, if that return code is non-zero, I think if we assert on that fail immediately, that would be a safe practice, right?
Say that one more time.
In one of the slides, it was suggested that we should not use asserts as a way to validate inputs. But in my understanding, if your validator function returns like a error code, non-zero, non-successful error code, asserting on that seems like a good idea to me. Like it will immediately fail if the input conversion fails.
I think it comes down to memory access as well. So if you're going through the motion of assert,
it's going to be harder to figure out some of those issues. Failing fast, like we're doing the bounds checking, the integer checking, the null dereference, null anything. It shouldn't be handled in an assert. It should fail early.
Thank you.
Hi there. I come from the games industry, and we're not so much worried about like external people, trying to like modify our programs or anything like that. But we're more worried about if the user of the program is actually trying to modify the executable and change the behavior of it. And I'm wondering if how much of what you're talking about today is sort of applicable for this sort of situation.
Yes. Before Microsoft, I was actually trying to interview for EA and their anti-cheat engine. So what's funny is that a lot of these exploits that you see that are used in malware bubble down to anti-cheat hackers. And so they'll use the same privilege escalation exploits to gain higher privilege, get kernel privileges, so they can turn off features of the anti-cheat engine or have full control over the game itself and being able to modify those memory locations to do like the hitbox, automatic hitbox changes.
Thank you.
Hello, I'm asking for some comments. Like, I'm wondering, like, what's your idea that if, for example, C++ magically become like memory safe? Do you think, as you mentioned, like this is a race between like offensive and defensive, right? So, do you think we will have like less vulnerability, or we will still have a lot of like security issues, just that they are now issues not related to memory safety, but related to other like risk condition or like just logic errors? What's your opinion on this?
If it was possible to get rid of all the memory safety issues, it could, that could happen. But, attackers are going to find creative ways to get around that. And we've seen that over the years with all these new introductions of fixes. So I can't see that happen. And it can be the lowest bar possible, like you're loading a file into memory and not checking it. It doesn't have to be C++ related. So I think that problem is always going to exist, and why I'm always employed. So.
Yeah. I'm asking because like people attack C++ a lot because C++ is not a memory safe language, and I also kind of agree that like even if we get rid of memory safety issue, we are still vulnerable to a lot of other issues like risk condition, like logic error, whatever.
I think it comes down to like what risks are you gonna accept, right? You're having to deal with security over performance, or security over memory allocation. You have to define what your attack vectors are, and try to work around them with the language that you choose. And there's going to be some folks that I just really like to write in Python, or I really love to write in C. We have all these different languages to choose. I don't see C++ phasing out anytime soon. So.
Yeah. So like my point is so you agree that like memory safety is not like kind of the blocker for the safety of like programs. It's just that I think it's just that like memory safety is most vulnerable, such that people use it to like to exploit our programs. But even if memory safety issues are like solved once and for all, we are still vulnerable to other like issues.
Yeah. I mean, we've always had that human element, the human developer, right? Maybe if we get into automatically generated code, maybe that would change over time. But we still have that attack vector, which is the human. So.
Well, thanks.
Mm-hmm. Oh.
Hi. Thanks for the talk, and thank you for sharing a lot of malware that maybe use some kind of kernel drawback and have made some attack. So my question is, for the embedded system, sometimes we don't have kernel, and also we may have something different like TE, which already isolate memory. So do you think we should have different kind of mindset for the embedded system?
Yeah, I think with embedded systems, from what I understand, it's not my forte, but it's going to be side channel attacks. So that's probably the most I've heard for hardware or embedded safety. I would focus on those areas.
Okay, thanks.
So a lot of the threat vectors you mentioned, like network traffic and deserialization, those frequently become interrelated, right? You're like trying to deserialize network traffic. In C++, you very frequently need to use memcopy because of the type punning problem. So aside from like fuzzing, do you have any recommendations on how to be safe when you're trying to deal with like, packets on a wire where you need to do things like memcopy?
Yeah, I mean, there's a safer, function to memcopy. I think it's memcopy_s, or the other way around. I haven't done it in a while. But when you're doing any type of parsing, especially from the network, you want to make sure you isolate that into its own memory space in another process, and then take that information and send it to another process to handle it. So the main thing is being able to isolate these different portions, reduce the complexity, and make the architecture a little bit simpler to isolate the untrusted input, right? We don't want failures with untrusted input, like an RCE coming in and attacking the rest of your program.
Okay, thank you.
Mm-hmm.
Hello. So going back to the rule of two, if you look at how C++ is part of that, it's an automatic shackle on C++ because of the memory safety. And I'm not sure how aware you are of C++ profiles, which adds automatic memory safety and type safety to the language in the future. How do you see that changing your perception of the rule of two and C++ being perhaps a safer language?
If you can get developers to adopt it, that's the issue, right? And having those rules and regulations within your company and guidelines to make sure that's like a standard. So it's got to be about the adoption of it.
Yeah, of course.
Yeah.
It's like if you were using unsafe in Rust. Welcome to the club.
Right. Or interop between C++ and Rust. We haven't looked at that yet. That's actually on my hackathon to-do list.
Thank you so much.
Yeah.
So when you were explaining about thread boundaries, like user inputs, and like you in the same slide you had deserialization, deserializers. Could you expand a little bit more on that? Is that like, did you mean that as in like deserialization libraries or like serialized input, or kind of like what did you mean exactly?
Yeah, when I mean deserializers, thinking of like marshalling bytes. You're taking up bytes and putting it into a struct. You're taking text, putting it into a struct, kind of like you're taking a file or JSON, deserializing it into a struct to be used. That movement of data is what I meant by deserializers.
So you meant the libraries themselves, or?
It can be the libraries itself. Sometimes people roll their own deserializer, so it doesn't always have to be a library.
Okay, all right, thank you.
Hey, really good talk. Thank you so much for that. So I wanted you to touch a bit more on the great arms race you mentioned. So in gaming, for example, there's a lot of kernel-level anti-cheats that are coming out. And game companies like Riot, for example, added in Vanguard last year, kernel-level. And I read somewhere a couple days ago that Microsoft is discouraging the use of these kernel-level anti-cheats. Can you comment on that? Like, how do you see the arms race evolving in lieu of that?
Yeah, anti-cheat is similar to endpoint detection offerings like EDR. And so what a lot of these do is that when a game is being ran, it hooks into those functions and manages the memory outside, like in a kernel driver. And when you're doing that, you're bypassing the security promises of what Microsoft, offers. So it's just like antivirus. There's a whole thing about antivirus being, it's just as bad as malware, because it's doing the same thing. Same with anti-cheat. So trying to get people out of the kernel is a goal.
Right. So then how do you prevent bad actors from getting into the kernel?
Well, one of the things that we try to do is, running drivers that are not validated. We have a whole driver program to make sure that they're signed, they've gone through the validation process, but it's all going to be about how the user kernel boundary is managed, right? How the structs are being managed in kernel, all those input validation problems. With human developers, there's always going to be a chance where you've got this new kid trying to do a user mode, struct to kernel, and they don't know that they're supposed to do the input validation,
right?
Based off lack of experience, right?
Awesome. So, thank you so much. Really appreciate it.
Mm-hmm. Any other questions? Okay, great. Well, thank you for coming.